This is Lab 2 for Physics 2, Charge Tape Revisited. Introduction. The purpose of this lab was to produce a computational model of two charged tapes exerting an electric force on one another. Some fundamental physics principles involved in this lab. Charge distributions can be approximated by an arrangement of infinitesimal point charges, in this case linear, since charge is distributed along the length of tape. The goal of this lab is to compare a point charge model to a linear charge distribution model. Can we get a more accurate estimate for the charge on the tape using a more accurate model? This is the conceptual model for the lab. Each piece of tape has the same constant linear charge distribution. A linear charge distribution can be approximated by splitting the tape up into a series of small point charges, or DQs. If we sum the electrostatic force interactions between all the point charges on one piece of tape with those on another piece of tape, then you can estimate the net force on one piece of tape. If you know the force of gravity on one piece of tape, then you can adjust the charge density on both pieces of tape until Fe equals Fg. The charge at that time would be a more accurate estimate for Q than the point charge model we used in the first lab. And in this case, the system would be the upper tape and the surroundings would be the lower tape and the earth. This is the first part of my code. The first thing I did was set physical constants, including K, G, the mass of the tape, and the charge on each piece of tape. I then created a function to find the electric field at an observation location due to a point charge. I then used the given function to create a line of charge approximating an object with a linear charge distribution. In this case, that was the tape. I set the DQ quantity, how many point charges to place in a line to make a charge tape object. I then created both charge tape objects using a line charge function. Define the visual scales for the Fe, Fg, and E fields, which will be useful when we actually visualize the forces using arrows. The net electrostatic force in each DQ in the top tape due to every DQ in the bottom tape is calculated. And then those calculated electrostatic forces on the top tape DQs were summed to find the net electrostatic force on the top tape. Then the force of gravity on the top tape was calculated and the arrows were displayed and the results were printed for the net electrostatic force and gravitational force. These are the results I got from my lab. I used 100 point charges to represent each tape. I adjusted Q until the force, the electrostatic force was equal and opposite to the force of gravity, and Q, when that was the case, came out to be 2.6 times 10 to the negative 8 coulombs. This was notably greater than lab 1, where the charge on each tape was estimated to be 1.3 times 10 to the negative 8 coulombs. Some observations from the lab. As DQ increased, Fe seemed to approach a value or limit. Fe decreases as DQ increases, which makes sense because more of the force vectors are horizontal as the charge becomes more distributed along a line, and the horizontal components will cancel. In other words, less electrostatic force on each DQ is contributed upwards in the direction of net electrostatic force. Because electric force is less efficient in a linear charge distribution than in a point charge, greater charge density on each tape is needed to cancel out force of gravity. Some assumptions we made in our lab. We ignored other possible forces than the force of gravity and the electric force, like air resistance. And we also assumed that each tape had about the same amount of charge evenly distributed along the length of the tape, even though it might not have been the case. And then the lab questions, what if we had modeled each of our tapes as a single point charge? If we did that, then our estimated charge on the tape would be less than the value we would get for a line charge model. Why do these estimates differ? This is because some opposite horizontal components of the electric force cancel, meaning a greater charge is needed to produce an electric force that is equal and opposite to the force of gravity. The line charge value is more likely to be closer to the real value, since in real life, the charge is approximately linearly distributed on the tape. Conclusions. Charge distributions can be approximated by an arrangement of infinitesimal point charges, in this case linear. This charge is distributed along the length of tape. To find the electric force between two line charges, find the sum of all the electric force on each DQ on one line charge due to each DQ on the other line charge. Opposite horizontal components of electric force cancel, therefore a greater magnitude Q is needed in a line charge model versus a point charge model to produce the same electric force.